Good morning. This is going to be our look at the chain rule from section 11.4. We will do a little bit of work on this in class as well, so we're going to take a little bit more of a low-tech approach. We're just going to talk our way through this rather than using a presentation. So let me find my that one out. So what we want to think about is what happens when we have a function. And let's start off with this function 2x plus 3 squared. Now algebraically, how do we process this if we are going to plug in a value? Say we want to find what is f of 1, so we're plugging in 1 for x. Well, we start inside the parentheses, right? We plug in the 1. So that's what we do first, is the inner part of the function. And that's what we want to focus on, is the functions we're going to be talking about have an inside and an outside function. Really, we want to think of them as two separate functions. So when we see this power function, we see a linear function inside with a power function on the outside. Go back to here. So we do that. 2 times 1 is 2, plus 3 is 5. So we apply that. And then finally, we do the outside, so we take 5 and we square it. That gives us 25. Now, how does this help us in thinking about the derivative? When we take the derivative, we've got to kind of do the same thing. So let's come over here and let's see what if this makes sense. Following, we kind of start on the inside and then we do the outside as well. And notice the outside, the inside's still in there, right? So what we're going to do is, let's do this in red. So we're going to take the derivative of the inside function, 2x plus 3. Its derivative, just this part, is the 1 comes down. 1 times 2 is 2. So there's the derivative of the inside function. Let's see what happens when we multiply it by the derivative of the outside function. And now what you want to think is this is a big parenthesis squared. So what are we going to get for the derivative of the outside? This 2 comes down in front, is multiplied by the function, the thing, the parentheses, with nothing changed. It just, because what I was going to do is think about it. If you have a glove on, nothing inside changes. So that glove protects you from anything happening on the outside. So think of those parentheses as a glove, as a protective barrier from the outside world. So that inside doesn't change. Okay, and then what happens to the exponent? We subtract 1 from it, so this becomes to the 1 power now. And what we've done is we're proposing that this is the derivative. So we might finish off by saying that this is 4 times 2x plus 3 to the first power, just like that. Now we could distribute this, and I'm going to do this because we're going to do a check on this to see if this process works, of taking the derivative of the inside part, boom, then taking the derivative of the outside, which is kind of looking at these parentheses as a bubble, a protective bubble. We should understand that with COVID going around. We're supposed to stay in our bubble. We're protected from the outside, anything that's happening. So only the stuff on the outside happens. So let's distribute the 4 through. So 4 times 2x is 12x. No, I was jumping. I was thinking of the 3 already. 4 times 2 is 8. It's only 8. It's always been 8. 4 times 3 is 12. Yes. Okay, so that's its derivative. Let's do this in a way that we're familiar with, because this is we're just proposing, hey, that sounds like it works, you go from the inside and then you do the outside last. Let's get the inside derivative and then let's multiply it by the outside derivative. We just sort of made up a rule, but does it work? And of course, hopefully you know that I did go through, I've got math was one of my majors. Education was actually my primary major, has always been, but I do have a degree in mathematics as well. So let's do this. Before we take the derivative, we're going to FOIL it out. Right, this is 2x plus 3. So we FOIL. So we get 4x squared. We're going to get 2x times 3. That's going to give us 6x. Here's another 6x, so that gives us 12x. And then the last is going to give us plus 9. Now, we've got this just as a sum of terms, and so we can apply the rules we already know. 2 comes down, 2 times 4 is 8. Subtract 1 from the exponent, that's x to the 1 power. 1 comes down, 1 times 12 is 12. 1 minus 1 is 0, x to the 0 is 1, so that's it. Whoa, look at that. The derivatives are the same. So why don't we just always do this? Well, what if we have a larger power than 2? What if it's 3 or 5 or 100? We certainly don't want to try to multiply this out every time, because while it can be done with a binomial, there's a theorem for doing it, it's tedious, and we end up with a lot of terms when this process of taking the derivative of the inside times the derivative of the outside. So again, this was the derivative of the outside times the derivative of the inside. This works as well, and what we'll do now is we'll just get some practice using a few examples that will help us get used to looking at functions, that there's an inside function and then there's an outside function. We take the derivative of both of those sort of separately and multiply them together. And now when we're doing the outside function, we will see the original function remains in there, because remember, it's in that glove, it's in the bubble of the parentheses. Okay, so let's look at something a little more challenging where we will need this. And incidentally, the next couple of sections we do, we'll look at logarithms and exponential functions, and this is where we really need them, because those functions typically have an inside part that is a polynomial or something. It's more complex than just x. It's not just the natural log of x. We're going to look at the natural log of some function of x. We're going to look at exponential functions where the exponent itself is some kind of a function. And so we're going to need this, and we're going to practice this, but this is going to give us the theory, the process, the technique we need to go through at least the next 3 sections. And then of course we'll be applying this, and with this chain rule, the product rule we've already got, the quotient rule we've already got. When we put all those together, we really have the means to get up just about every type of derivative we're going to need. So let's make a new function. Let's go ahead and go with the red. Let's say g of x is 3x squared minus 5x plus 4. Okay, and again, I'm just making these up as examples. Let's put it to the minus 7th power. Now, try to get this out of the parentheses. No way. You could write this as 1 over, but what I'm going to show you is the beauty of taking this chain rule. We do it in steps. Okay, so the way we go about doing this, let's switch a color, is I'm going to first take the derivative of the inside, because that's how we process functions. We go from the inside out. Now when you read the book, the theory they went through and formalized it, they always take the outside function derivative first, and then they multiply by the inside function. That's what maybe makes it a little difficult to learn, is once they dressed it all up, they lost the impetus of how we really do this. We really start from the inside first. So for these examples, I'm going to try to keep it where we take the inside derivative first, and we'll put it up front. So we just, whatever's in here, let's take its derivative. 2 times 3 is 6. 2 minus 1 is x is 1, so that's x to the 1 power. This 1 comes down, so we get a minus 5. 1 minus 1 is 0, so that's x to the 0 power, which is 1. And a derivative of a constant is 0. So that's the derivative of the inside part. Apologize, my wife's been coughing, I've been coughing. I hope it's nothing. I hope it's just a cold. These days we don't know. Okay, then we're going to multiply that times the derivative of the outside, and what we want to see, this is bubble to the negative 7th power. So bubble, this whole monster just comes down just as it is. Remember, it's in the glove, it's in the bubble, nothing's going to touch it. I wish we could say that about the virus going around, that we had some kind of guarantee, but we just don't. Now remember, go ahead and change colors here. This exponent is going to come down in front. That's how we do an outside. And then we're going to subtract 1. Now notice, since they're both negative, it actually is going to become negative 8. Okay, so the negative 7 comes down in front. And then the exponent is going to become to the negative 8th power. Boom, there it is. Now, we certainly don't have to multiply it all out. If you wanted to, you could take the 7 here, but you still are not going to be able to deal with this minus 8 power, although what you will sometimes see, so this is the derivative. And I want to show you from the test, when you're taking a derivative, you really need to have your function here. You need to say this is a derivative. You can't just write it and say, make everyone assume. Although some of you've done that. We'll take a look at those, but you really need to be, in showing your work, showing, hey, this is the derivative of g of x. Okay, so I'm going to distribute this negative 7 through. Negative 7 times 6. It's going to give us negative 42x, and then negative 7 times 5 is going to give us a positive 35. What I'm going to do with this negative exponent job is move it down into the denominator. It just makes it look pretty. Again, both are correct. We can use both for, we can use both still, but then we just have 3x squared minus 5x plus 4 to the positive 8th power now. Okay, so we could say that's a nice, pretty final derivative. And it wasn't too bad. You're taking the derivative of an inside part, nice and clean. You're taking the derivative of an outside part. So you just, that's really the whole lesson today. Identify the inside part, take its derivative. Identify the outside part, take its derivative, multiply the two. Okay, and notice when we're taking the derivative of the outside part, it's in its bubble. Nothing happens to what's in here. When we're taking the derivative of the inside, of course, it's like taking off the glove. Now we're doing something with the inside function. And we're doing it in the process that we would for evaluating a function. We do the inside first, and then we do the outside. If you read over the lesson in the text, which I encourage you to do so, it does give more explanations, but they quickly go to taking the outside derivative first and then the inside, which you could think of it, makes sense. The outside's accessible, and then you take off the glove and do the inside. But I just want to see it, which is the way I've always taught it. I want to see if this maybe is helpful, because chain rule is one of those concepts that is a little more difficult to pick up on. And as I read through, one thing I like about this textbook is it started it off with kind of an exploration of that. We start in the inside and then go to the outside. So let's see if this helps. and this is basically all we need to be able to do, you know. And the thing is we can take derivatives of whatever higher powers we want, because we're not going to expand things out, we're just going to do that. And for this lesson, that is pretty much all we need to worry about. Let's see, it's a little bit of time. Let me pull up, come over here, let me pull up the homework and just take a look and see if there's another example that might be beneficial. It's kind of similar but a little different. Yeah, I guess we could do, let's change colors here. Let's go back to blue. And let's do something like h of x. Now, let me just check real quick. The chain rule can be combined with either the power rule or the quotient rule. We'll do one with the quotient rule because there is one in the homework that's like that. It could get a little messy. And then just to let you know, 7 and 8 in the homework are a little bit of a stretch. I want you to basically, but just think you're just going to take the derivatives as we usually do, and then they've got the part on the outside. We'll explain those after we get by them. But 7 and 8, if they don't pass your first muster, we can explain those. They're technically not more difficult to do. Okay, so if you get through 1 through 6 is really what I'm going to do, and I'll do one like 6 because it's got the quotient rule in there. I'm just going to give you one more like we'll just do something like this. Okay, now again, you might start looking at this and you think it's going to be a quotient rule because it looks like a rational function. I guess it is in technicality, but again, the first step we're going to do is we want to focus on these exponents just like we've done. So let's move it upstairs. So let's call this 2 times 5x to the third plus 8x squared minus 4x to the negative 3. So we remember to do that. When we move it upstairs, it becomes opposite. That negative is not so much think of it as a negative number, but think of it more as an opposite operation. Remember, exponents is repeated multiplication. That opposite says we're doing the opposite operation. We're repeatedly dividing. It's the best way to think of it. It took me years to come to that conclusion, but that's what works. Now, the thing is in the front, we would use a product rule if this had an x on here. If this was 2x, we would have to do a product rule thing here, which we will be doing before we're done with all of this. Not in this lesson, though, okay? Since it is just a number, it is a constant multiplier. And so we can't distribute it because we've got this exponent, but it just tags along for the ride when we take this derivative. Okay, so as we take the derivative of this function, remember we're just going to identify the inside part. Well, that's the part inside the glove, inside the bubble, inside the parentheses. There it is. We are going to take that derivative first because we're working from the inside out. That's the way we do functions. Okay, so 3 comes down. 3 times 5 is 15. 3 minus 1 is 2. 2 times 8 is 16. 2 minus 1 is 1, so that's 16 to the 1 power. And then this 1 comes down. 1 times negative 4 is negative 4. 1 minus 1 is 0. X to the 0 is 1. So that's the derivative of the inside part. Now, since it's multiple parts, as I think we've been doing that before, we want to put a parentheses around it. because that whole thing is an inside derivative. It's going to multiply by the outside derivative. Okay. So for the outside derivative, we've got bubble, hand, glove, everything inside here raised to the negative 3 powers times a 2. So let's just, just treat this as a big old thing. And so we could just go ahead and write it down now. It's like a big old X. They also use something, they kind of do U substitution. They just call this thing some function of some U, a U function. Sometimes that's helpful, I think, but after you understand it, it means more. When you're trying to do this, it's just an extra letter to kind of scramble with. So I just want you to see, we take this whole inside thing, and now we're just working with the outside part. So we're going to take this negative 3, bring it down in front. 2 times negative 3 is negative 6. And again, this is all getting multiplied. So it's not subtracting now, it's still multiplication. So that 2 became negative 6 because this 3 came down. And then remember, we're going to process this by subtracting 1 from it. Negative 3 minus 1 gives us negative 4. We're done. That is the derivative. Again, you can dress this up a little bit because this has an exponent of 1 on it, so we could distribute this 6 through. We get large numbers. I'll let you do that if you want. Again, I just sort of made this up, so but it's very similar to the types that are in the homework. You should see one very similar to this. I'm just going to leave it like that. I don't want to take the time to take 6 times 15. Can't do it in my head, and then what would and I don't want to bust out the calculator right now. I want to focus just on this process. Derivative of the inside, boom, times the derivative of the outside. With that sort of that bubble approach, everything inside just stays in there. So then we get 5x to the third plus 8x squared minus 4x. Again, when I move it back down, it becomes a positive exponent. So again, we could write it this way. The top way is fine too. But just get some practice with the algebra skills. Get some practice with writing it out this way. And we'll be all good. Okay. So I've got one more example, and then, like I said, I pushed it a little bit tight on time. Class will be starting here pretty soon, but I'll get this posted before class. So let's take one look at a function that involves both the chain rule, and again, this is put this off a little bit, but and remember, if you've got if you've got a square root, that's just change that to a 1/2 power. Okay. So now let's look at this function. Let's go with what should we call this? M of x, Mike of x. I don't know. Why not? Let's go with 2x minus 4. Oops. Well. Parentheses there yet. 2x minus 4 over 5x plus 3. And this is all raised to the 5th power. Now, using our technique of finding the derivative, the derivative of the function. Remember, we're going to take the derivative of the front part, of the inside part. That's going to go right here. But that's all that we need to use the quotient rule. Okay, so I'm actually going to, that's going to be probably the hardest part of this whole thing. And then we multiply this times the derivative of the outside. You're going to see the outside is a very easy process. Bring the 5 down, subtract 1, it's going to be to the 4th power. The inside doesn't change because it's in the bubble. In fact, let's go ahead and write that. Maybe that's why they start writing this one down first, is because as we progress, a lot of times, let me change back color, the outside function oftentimes becomes actually the easier part. So the 5 comes down, so we're multiplying times 5. The inside is still the inside. we subtract 1 from the exponent. 5 minus 1 is 4. So there's our outside part. Now we got to come back and do this inside part. So while I told you we don't have to worry too much about testing from test 1, we are still applying some of the content that we learned. So remember, with a quotient rule, we have a numerator and a denominator, and when we take its derivative, it's the derivative of the numerator times the denominator minus, a few of you I saw were putting a plus here. This is a minus the numerator times the derivative of the denominator all over the denominator squared. And what's the numerator? 2x minus 4. So we come over here, we've got 2x minus 4 for n. N prime is going to be 2. D, the denominator, is 5x minus 3. So the denominator, the derivative of the denominator, is 5. Okay, and now we just put our pieces together. So it's going to be 2 times 5x minus 3 minus derivative of 5, so we go 5. We could put it first, or you could put it second. N is 2x minus 4. And again, you can multiply that out or not. Derivative of not derivative, the denominator squared. Okay, so that all would, maybe I should have just wrote it in there. And if we have to use this, and that's what we start doing, is just as we use the function to come up with input and output values, we will analyze it with a graphing calculator. If we need to do something with this derivative, because it gives us, it's marginal cost or marginal something, so we're making a business analysis, we would still put this function in a graphing utility to come up with either a table of values or a graph to kind of get us a projection of what's going on in the future. Should we buy more or should we buy less? What should we do? Decision making, right? So it's not as complicated. We don't have to. Okay. Now, with that being said, since this is going to be our last example for today, let me just go ahead and do that. Distribute through, so you get 10x minus 6. And then this one, you're going to take a negative 5. Negative 5 times 2 is going to give us negative 10x. And the thing you'll see is oftentimes, because you've got this, the way the derivative is, oftentimes if you've got two linear equations, since this is derivative of the one, you get those canceling out. Okay, and then we get a negative times a negative, so we get a plus 20 all over the denominator. So if you see it simplified, sometimes it's nice to do that. So the 10x are going to 10x minus 10x, that does cancel, and then you've got a negative 6 and a positive 20, so that simplifies down to positive 14. So if I'm going to rewrite it, that's a lot cleaner to write, over 5x minus 3 squared. So that is the derivative. So we could leave it like that. And then again, if you wanted to, you could move this, because this is to a first power. You could take 5 times 14. But that's the thing with algebra. There's usually something you can do, and you might decide to do something different than I do. So our answers might look different, but they should both be correct. And that's why I'm gonna, I want you to, on the exams, I'm gonna give you access to them afterwards, so you can review. If you see something that looks like, hey, I should have got credit for it, take a screen snap, send it to me, explain it to me, or talk to me during office hours with it. We'll take a look at it, and if it makes sense, we'll go with it. If it's, a right answer is a right answer regardless of form. All right, so I'm gonna stop here. We're going to post this video. If I can find my software, here it is, it's over here. And then I'll see you in class in a few minutes.